Okay, hello everyone. Welcome to the first webinar by IEEE PES DALI Task Force, Data Center and AI Load Integration Task Force. So today we're very happy to have Dr. Min-Seung to present the kickoff webinar with a brief introduction on DALI and also some of his recent research work on AI load dynamics analysis. So I want to first start with a couple of housekeeping notes. We have a link for signing up for the task force communication. I'm gonna send it in the chat box so that everyone can see. Yeah, it's a Google sign up sheet, which requires you to have a Google account. If you don't have one, please feel free to send me or Min-Seung an email, and we'll be sure to add you to the email list. So this task force is organized under PES SBLC Technical Committee, Smart Building Load, and the Customer Service Technical Committee. We're very grateful for the support from the Technical Committee. And as Min-Seung will introduce later, there we have some plans on different directions, and would love to get your input for us to come up with the technical reports and final documentation for this task force. So yeah, we look forward to working with you on this task force. Yeah, I think that's it. So let me introduce Min-Seung. By the way, I'm Hao Zhu. I'm an associate professor at the University of Texas at Austin. And so today's speaker is Dr. Min-Seung Kao. Dr. Kao received all his degrees from Yonsei University. He is currently a postdoc fellow in UT Austin, and he's also the secretary of our task force. Thank you, Min-Seung. And he is working currently on data center integration and renewable dominated power systems and the stochastic stability analysis. So without further ado, I would like to ask Min-Seung to start the presentation. And if you like to stop for questions at some point, I think that may be helpful. So we can ensure to have some interactions at different point of the next hour. Yeah, thank you, Min-Seung. Please go ahead.
Thank you for the nice introduction about myself. So yeah, as how introduced very well, my name is Min-Seung Go, and currently I'm a secretary of this task force as well as the postdoc at the UT Austin. So in today's presentation, I'd like to first briefly introduce of our task force, the DALI task force, and then I'll move on to our recent works about the wide area oscillation, which will be caused by these kinds of large loads and how we can mitigate this kinds of oscillation based on the power smoothings. So to move on to the overview of this task force. So this task force is the data center and AI load integration task force. And we aim to prepare and deal with the continued integration of AI data center loads or any other type of large loads. But specifically for the data centers, we will mostly focus on the data centers which should handle the generative AI or the large language models, since these kinds of data centers will require a lot of power consumptions to train or handle these kinds of large language models. So in the task force, we have two co-chairs, which who are Hao from UT Austin and Julia from ISIC. And as I mentioned earlier, currently I'm a secretary of this task force. So if you have any questions or suggestions regarding to this task force, please feel free to email to us. And there are a lot of members in this task force from academia, utilities, ISOs, industries, and research organizations. So I hope and expect that there will be a lot of constructive discussions and outcomes from this task force. So for the planned activities and deliverables of this task force, we will have a regular webinars like today's meeting on the last week Friday of each month. So currently we are planning to have the next meeting on 24th of April, but it could be delayed to the 1st of the March, and we will send an email to you for the participants in the email list. And we are also planning some panel sessions during the PS General Meeting from 2026 to 2028. And for 2026 General Meeting, we already accepted for the panel sessions, so we will have it for this year's General Meeting. And we will also plan to open this panel sessions for the upcoming General Meetings also. And we are also planning to submit some transaction papers as well as a final report which summarize the overall activities of this DALI task force. And moving on to the technical scope of this task force, we are actually divided these kinds of scopes into three large tasks. So the first task would be the AI data center modeling. Second would be the grid impact and stability analysis from these AI data centers. And final one would be related to the interconnection requirements. So for the modeling test, we can first establish a taxonomy of data center models, and we can also review or improve the current or new type of positive sequence EMT data center models, as well as the AI workload load consumption model. And for the grid impact and stability analysis, the first or the most interesting task would identify the potential stability risks which you could be caused by these AI data centers, and then analyze of this data centers impact, including the facilities themselves, as well as the first response of these AI data centers, or the lumping and workload profile of these data centers on the grid stabilities. So although I have only mentioned about the stability in the second point, but more a lot of ranges could be included in this task. So from some static analysis or steady state analysis could be also included in this second task. And for the finer technical scope, I think for this one, it would be more likely to recommend or improve the current interconnection standards or the planning tools of the current system operators practice. And in these kinds of practice, which they can include some kinds of technical requirements to maintain the grid stability under the high penetration level of the data centers. And then these kinds of things could also include the mitigation options or the mitigation strategies to help to increase the stability of the grid. So moving on to more specific scopes. For this scope one, which is the AI data center modeling, there are already some interesting and hard workings from the utilities and the system operator sides. So in the case of the positive sequence model, there's already an initial model about the AI data centers, which is called as the PRC1 model. And this model can be used in the recent PSS, the commercial tools such as the PSSE. And this kind of model is based on the electrical vehicle model, which was previously used. And there are also some ongoing improvements about this PRC, the positive sequence AI data center model. And in the case of the EMT model of the AI data center, there was a recent report from the PNNL, and they also shared the PSCAD model, which can be used for the AI data center. So I think that this could be very helpful for the researchers who like to use analyze the EMT-based analysis of these AI data centers. And another interesting things or another distinctive thing of this AI data center model specifically at the positive sequence level, is that the normal operation of the AI data center could arise some stability shifts into the grid. So how we can model the steady state or normal operation behavior of the AI data centers need to be further discussed so that they could be incorporated into these kinds of dynamic models. And moving on to the second scope, I would like to first start from explaining the below figures. So, um, as I mentioned earlier, the facility itself of the data center, the first response, and the workload profile of these data centers can affect the various stability issues. And when combining all of those issues, I think that the data center can affect all categories of degree stability, from the resonance stability to the frequency stability. And also, the recent NERV report has categorized the likelihood and impact of this risk from this emerging large loads. So I think that the below two reports can help you to understand and to see how the North America in the case of the in North America, how the NERC is showing these kinds of risks. And as I mentioned earlier, there are also some steady state issues from long-term planning, harmonics, and balance reserves. And I think that this could be eventually result in some kinds of penetration level or the available penetration of these data centers. So all of these kinds of things could be within the scope two, the grid impact and stability analysis of the data center. And final part is the interconnection requirements. So there are also some upgrades or updates about the interconnection requirements from the ISOs currently. So as you can see from the left figure, recently there was some updates about this large loads related to the voltage write-through or the frequency or first write-through requirements, like the left figure. And in the case of the PNL, they also suggested some possible energy storage system deployment points at buy points. So it would be also an interesting direction to analyze which deployment point would be most beneficial for the grid stability or grid perspective. And in the case of the interconnection standards like the right table, there has already been some kinds of requirements of the active power ramp rate limits of these large loads, but still there are some ISOs or regions which do not have this kinds of detailed ramp rate limits. So how we can set the ramp rate limit, which ensures degree stability, would be another interesting stuff. And in the case of the oscillation, because the fluctuations, the magnitude or size of the fluctuation itself is important to determine the oscillation severity. So how we can set or what would be the maximum fluctuation limit, which can ensure the frequency or smaller stability can be very helpful for determining or improving the current interconnections. So giving some kinds of recommendations based on the research outcomes would be the main topic of this scope 3. Yeah, so this was the introduction of the overall tasks or technical scope of the DALI task force. So I think we can have some, if you have any questions about this task force, I think you can first ask a question at the current stage.
Hello. Thank you for your presentation. Very, very interesting introduction and very comprehensive. We have seen a lot of task force like the ESIC task force and the NERC task force. How do you envision differentiating the task force from the other task forces? Thank you for your time.
Yeah, I think that's a very nice question. Yeah, how we can.
Go ahead, Min-Seung.
Yeah, so actually the participants in the ESIC and the NERC task force are also a member of our task force. And so I think that the overall directions should align with the directions of the other task force. But I think that the key distinctive point of our task force is that there are some more participants from the academia side. So I hope that we can give some the scope 3 would be the largest difference from the other task force, because we can give some research outcomes which would be required for the other task force. So the requirements which is specified by the other task force, and then we are planning to give the result or the solution for that kind of requirements. I think that's the most different point of the task force.
Yeah, thank you, Min-Seung, for the nice answer. So I just quickly add here that, so IEEE PES task force is broader in terms of the type of participants. Yeah, we are also part of ISIC discussions. I think most of people are coming from consulting and industry. So yeah, definitely we would love to have more academia support and national labs and the R&D to focus on the R&D aspect. So usually the deliverables for IEEE task force is technical report and also possibly transaction papers. So I think this is also a different aspect for our task force. Yeah, thank you for the great question. Yeah, so I think Robin, would you like to unmute yourself and ask question? I can unmute you if you, okay.
How's that? Yeah.
Yeah.
There's two separate questions. Will the possibility of using these systems as black start units be considered? And the second question is, what sort of models, test models, because obviously the system interactions are vital. And I know there's been some hypothetical models, but I've become a huge fan of using open source models like the open infrastructure maps, where we could actually create fairly good models of any part of the world. To me, it's a shame that it's almost a year that has gone by since we had the Iberian blackout. So why we've got to break this logjam of taking so long to get reports out, and I'm proposing that we actually build typical power systems from the open infrastructure map models. So I just want to see if there's a scope for those two areas, building standardized system models as well as the component models, and also the possibility for black start. Those are the two questions, please.
Yeah, Min-Seung,
So
would you like to start with black start? Yeah.
So in the case of the black start, I'm not sure whether the large load could lead to the black start, but definitely there are a lot of stability issues, which it has been already discussed and reported in the North America. So if these kinds of issues was not handled very well, it could have led to the blackout. But since we are for some kinds of transitional operations of the system operators, we are already considering a large size of disturbances. So we cannot say that the AI data centers will always lead to the blackout, because as we can see from the Iberian blackout cases, there could be some potential risks which could even lead to the blackout cases. So I cannot ensure that the data centers would always lead to the blackout, but there could be always the possibility which can lead to the blackout and those kinds of stability risks. And for the open source model, yeah.
Sorry, no. The point of the question wasn't that it would lead to the blackout. The point was that given that you've got a huge resource there of many diesel units or many gas turbines, they could be a very valuable resource for the restart of the grid that was caused by somebody else. That was the whole point, is that I know their tendency is going to want to serve the local load, but there's also an issue that maybe they should defer that and actually provide a black start facility for the rest of the grid, so the rest of the grid could be served. That was the question. Thank you.
Yeah, I
Yeah,
see. Now I see.
if I can add on that, we talked to several data center owners and including tech companies. They are pretty conservative in what they want to do to the grid side. So I think this has to come with policy and regulatory decisions if this is required or if there's some strong incentive for that. So yeah, they would eventually abide because, as you mentioned, they have a lot of energy resources that on site that can be utilized. But at this point, I think it's not yet clear the pathway forward to for us. I would also quickly respond to the second part. So I think open access is definitely something all of us want to achieve in academia. So perhaps, one issue we encounter in this research is the real world data for data center is extremely sparse, if not none. So I think having sizable or scalable level of measurement data is largely missing in the public domain. And if there are anyone who could help us or this task force together to achieve that, we would really love to talk to you. Yeah, thanks. So I think I have last. So maybe this will be the last question before we move on to the technical presentation. Please go ahead. Last, can you? Sorry, we cannot hear from you.
Can you hear me now?
Yeah. Yes,
Brilliant.
please go ahead.
Yeah, that was wrong microphone setting. Well, hi everybody. I'm Laís Souto from the University of Bath. It's a mix of a question and a comment following on the previous question. I do think this compliance with grid code requirements, considering different potential applications of data centers and AI loads to this scope, should be part of this task force, especially considering the huge load they will introduce and the efforts made with other loads such as electric vehicles and other loads with demand response capabilities. So I do think this needs to be within the scope of this task force. And with this, my question is, how widely do we intend to cover these grid code requirements and what is already available for other load technologies?
Min-Seung, do you want me to repeat the question or reconfirm the question?
Yeah, I think I would like to reconfirm your question, please.
So I think, go ahead, please.
So the question is, to which extent do we intend to include compliance with grid code requirements in the scope of this task force, considering different supports that could be provided by data centers and AI load technologies?
I can start, and Min-Seung, feel free to add in. So I think this is also related to the first question about the NERC task force and this one. So as academic researchers, we probably would just submit an analysis case study results on the type of impacts of data centers on the realistic power systems. So the exact compliance and the regulatory decisions, I think is a lot of that happens with maybe NERC, which is the North American Reliability Coordinator. So they will probably, be the leader in that domain. So I think, as the focus here R&D, so we encourage a lot of more discussions on like different types of impact, time scale impact of data centers, which would with our goal of eventually helping the regulator and decision makers to come up with the exact policy for integrating data center. Yeah, thank you for that question. Yeah, so maybe we should move on to the next part.
Okay, yeah, then I will introduce our recent works about the grid oscillations and mitigations for covering AI workflows. So to start from the AI workload characteristics, as I briefly mentioned earlier, this AI workload shows a distinctive pattern from the previous or conventional industrial loads because they include the severe size of ramping, as you can see from the left figure, as well as the oscillatory or fluctuation behaviors. So these kinds of behaviors can induce severe stability issues at the grid. And specifically for the wide area or oscillation perspectives, the fluctuation behaviors itself will be the great concern because it could lead to the forced oscillation in the power system. And these kinds of fluctuations are arising in the multi-time scale, as you can see from the right figure. So the training iteration of these AI data centers could lead to the fluctuations, which could arise the inter-area or local frequency, local mode oscillations. And the training sub-loop can lead to some kinds of subsynchronous oscillations. And the gradient computation during the AI workload itself could lead to the higher frequency fluctuations, which can induce some problems at the rack level of the data center itself. So modeling these kinds of the AI data centers power demand or the fluctuations and analyzing their impact are very important things from the grid perspective. Yeah, and since we are aiming to analyze the wide area oscillations, we are specifically focusing on these kinds of frequency ranges. And in order to model the workload of these AI data centers, we first need to know or see how these data centers are generally composed of. So as you can see from the left figure, a lot of components are included in the data centers. And although the largest component or the key component of this data center comes from the servers, including the CPU and GPU servers, but there are other type of equipment such as the storage system, cooling system, or the communication systems implemented in these data centers. And as you can see from the right figure, currently the AI workload or the GPU server composition is around 10% of the AI data center, the core AI workload data centers. But for the generative AI data centers, this kinds of the fraction of this AI workloads is expected to increase to around 50% of the total data center load. So to characterize or model these AI workloads, we actually we need to model all of these different type of loads, including the non-AI workload and the non-server loads. But the fortunate thing at this point is that the non-AI, which means the CPU server and the non-server loads, such as the communication or cooling system, cooling loads, shows a more stable pattern compared to the AI workload itself. So in this work, we assume that this type of non-AI and non-server loads is a constant. So we can focus on modeling the AI workloads for modeling the fluctuations of the AI data centers. And when we look at the operational stages of these AI workloads, mostly, especially for the large language model, there are 3 operational stages, including the pre-training, fine-tuning, and inference. And when if I explain this stages from the large language model, the pre-training is to update the parameters of the large language model from the start by using a very wide range of data sets. And in the case of the fine-tuning, it is to change the parameters a little bit so that the using a smaller size of data set, so that this kind of large language model could be more specific for our intended objectives or tasks. And then the inference is to using this fine-tuned large language model. So just using the ChatGPT or those kinds of large language model tools would be the inference stages in this AI workload stages. And in the case of the inference stages from the AI companies or the users who use the large language model applications, it is better to handle these kinds of inference stages at the smaller data centers, which are located nearby the users. So since we are mostly looking at the large data centers, these inference stages or inference workloads would not be generally handled in these kinds of large data centers. So for this large data centers, we can focus on modeling the pre-training and fine-tuning stages of the AI workload. So when we look at how much power is required to train this kinds of large language model, you can check out this left figure. So in the case of the earlier models, it mostly require tens of megawatt, but it is expected to increase hundreds of megawatt in the future, and it is also currently there are some kinds of increasing pattern, these kinds of the power consumption required to train the large language model. So even for the large data centers, a single large AI training workload would dominate the overall AI workloads, considering the size of the power consumption required to train a single large language model. So we can draw some kinds of hierarchical composition of these AI workloads, like the right figure. So among the total power system load, there around 10 to 20 or 30, even increase to 30% penetration of data centers. And in the case of the individual data center itself, around from 20% to 50% of this data center load could be composed of the AI workload. And when looking at the AI workload itself, a single large training load could dominate or would take a large portion of this AI workload, while the remaining would be composed of the small training workload and the fine-tuning workload. So when we look at the characteristics of the training and fine-tuning workloads, both of them show fluctuating patterns, although they have a slightly different frequencies. So basically, we can model both the training and fine-tuning workload based on the similar mathematical basis, like the below figures and equations. So both workloads show the fluctuating patterns between the high power zone and the low power zone. And both workloads also include some variabilities in terms of the magnitude of this fluctuation, as well as the duration or frequency of these fluctuations. So when we compare these AI training workload and AI fine-tuning workload, you can see that the training workloads seems more like a sinusoidal wave, while the fine-tuning workload seems like the square waveforms. Because the fine-tuning workloads show a smaller variability in terms of the magnitude compared to the training workload. So in the case of the training workloads, so compared to the training workloads, if both the training workload and fine-tuning workload have a similar magnitude, the fine-tuning workload would have a higher possibility to induce the oscillations from the grid, induce the force oscillation from the grid perspective. But since as I mentioned earlier, the training workload has a much larger magnitude and size of power consumption compared to the fine-tuning workload, still the total AI workload would be dominated by the training workload's behavior. And in the case of the frequency, from the industry reports, it is well known that the AI training workload has already induced the 1 Hz oscillations. But these kinds of frequency could be different according to the various factors in the data center itself, as well as the AI model we are trying to train or fine tune. So if we are trying to train the large language model, we will require more time to train this or compute this training process, then it will lead to the lower frequency of these fluctuations. While or if we use more larger number of GPUs, we can shorten the time elapsed to require for training the model, and it will lead to the higher frequency of these fluctuations. So we model these kinds of fluctuation frequency, magnitude, and durations or duration ratios as random variables in our framework. So from the below table, you can see some example of these parameters, which are adopted for modeling the previous training and fine-tuning workloads. So this kinds of lower bound and upper bound is the boundaries where the previous parameters can be located at. And you can see that for the training workload, the boundary is set to 0.5 to the 1.5 hertz, while the fine-tuning workload is set as 0.3 to 0.7 hertz, which is slightly lower than the training workload. And in the case of the power demand, the parameter mu represents the deviation between the high power zone and the low power zone. So in the case of the training workload, there's a smaller deviations between the high power zone and the low power zone compared to the fine-tuning workload. So this also supports that if they have a same magnitude, the fine-tuning workload would have a higher possibility to induce the oscillations. So based on these kinds of workload models, so we aggregated the single large training workloads and the multiple small training workloads and fine-tuning workloads. And by aggregating them, we can generate these kinds of AI workload in the red lines. So if we compute the FFT on this AI workload and the large training workload, you can see that from the below figure, the most of the behavior or the frequency components of the aggregated AI workload is very similar to the large training workload, although there are some differences in the lower or higher frequency zones by the small training workload and the fine-tuning workload. And specifically in our study, we assume that the ratio between this small training workloads and fine-tuning workload is 5.5 and 9.5 and 0.5 ratio. So until now, I have explained about the overall modeling methodologies of our work. Is there any questions until now?
I don't see any hands raised, so please go ahead.
Okay. Yeah, then I'll move into the simulation part. So in this work, we analyze the impact of various system level factors and data center level factors on the wide area oscillation severity. And specifically, we use the Andes simulation tool. And the data center is modeled as just as a time variant load without some kinds of physical components, including the inverters or the DC systems behind the data centers. So, and we also tested this kinds of data center model in two systems, including the web system and the MPCC system. And for both systems, although the number of data centers are different, but we set that the penetration level as around 10% of the total load of each system. And each data center size is assumed to be 1 gigawatt based on the previous industrial reports. And moving on, when we included and implemented this kinds of load fluctuation model, because the basic frequency or baseline frequency we assume in this study was around the 1 hertz, these AI workloads lead to the force oscillation at the locomons around the 1 hertz. So as you can see from the left figure, there is a increasing or sustained oscillation, forced oscillation at 1 Hertz. But interesting point of this AI workload-induced oscillation is that although these kinds of oscillations are at the local mode frequency, they show some behaviors like the inter-area oscillations. So when we look at the frequency trajectories at this purple zone and the green zone, you can see that they have opposite phase angles. So there are some kinds of behaviors like the inter-area oscillations. And we also tested whether really these kinds of 1 Hertz oscillation really comes from the fluctuation of the AI data centers. So we computed the coherence between the data center demand itself and the system frequency response or system frequency trajectories. And you can see that there is a high coherence level at the 1 Hertz, which means that the dominant factor of this 1 Hertz fluctuation comes from the data center demand, while this 1 Hertz oscillation could be further aggravated or could be further amplified because of the systematic modal characteristics. In the case of the other frequencies, you can see that they have a smaller level of coherence, especially at this inter-area mode frequency, which means that although the data center demand has a lower amount of this or lower magnitude of this inter-area of these fluctuations at the inter-area mode, but it was largely amplified the system's modal characteristic itself. And this page shows the impact of the fluctuation frequency range, which I discussed in modeling the data center. So we tested the normal from narrow range of the fluctuation frequency to the wider range of the fluctuation frequency. And of course, the narrow range of the frequency generally leads to the higher excitation of the lochromon around the 1 Hertz. So you can see that the narrow range leads to the larger FFT magnitude in the local mode, in this case, in the local mode oscillations. But in the case of the wider range fluctuation frequency, you can see that there are some kinds of excitations or noticeable magnitude of FFT at the lower frequency level, which is at the inter-area modes. So from the middle figure, you can see that although there are some kinds of 1 Hertz oscillations are observed, there are some kinds of large patterns or the lower frequency patterns in the case of this wider frequency range. And when we compute the pseudo energy of these different fluctuation frequency oscillations, you can see that although there was a small magnitude of FFT in the case of this inter-area oscillation, but you can see that in the case of the pseudo energy, there's a larger amount or comparable amount to this 1 Hertz local mode oscillations. So this would be the reason why the system operators mostly are interested in these kinds of wide area oscillations because of this large impact on the wide area grid. And I'd like to move on to the impact of the geographical locations of the multiple data centers, which will be one highlight of our research. And in the case of the data centers, in the baseline case, we assume that the data centers are geographically concentrated, like the red circles in this right figure. But we compare these cases with the geographically distributed cases in the red triangles. And our first assumption or our first guess was that because the data centers are was that the geographically concentrated data centers would lead to the larger or severe oscillations because if they're concentrated, they would give some more reinforced impact on the oscillation or grid side. But the simulation result was the reverse. So there was a smaller magnitude of the oscillation in the case of the geographically concentrated cases, and there was a larger magnitude of oscillation in the case of the distributed data center cases. So you can see those results from this left figure, and this figure shows the Pernian analysis results where the x-axis shows the frequency level and the y-axis shows the damping ratio of each frequency, and the size of each cycle shows the magnitude of the oscillations. So compared to the concentrated case, in the distributed case, you can see that there's a larger magnitude of the oscillation is observed at the around 1 Hertz. And one interesting point between this concentrated and distributed cases is there is a noticeable difference in the case of in terms of the damping ratio at this 0.5 Hertz level. So although they have some similar magnitude of the oscillation at 0.5 Hertz, they have very different damping ratio levels. And we think that the reason behind this kind of result is that when the data centers are geographically distributed, they would have a higher possibility to excite the unstable modes within the grid, as you can see from the right figure. So these kinds of excitation of local or unstable modes would lead to the lower damping ratio in the case of the geographically distributed cases. And when we think about another reason beyond why the geographically distributed cases result in a larger magnitude of the oscillation is that when the data center loads are concentrated, there could be some kinds of aggregated impact from the power demand of those data centers. So there could be some cancellations of high frequency terms in the case of the concentrated cases. So that would be another reason why the distributed data center result in a larger magnitude of oscillation. So in summary, in the case of the oscillation perspective, the geographically concentrated cases is more stable compared to the distributed cases. But as you can see from the right figure, in this case of the in the concentrated data center cases, they are more vulnerable to the low voltage stability issues because basically they require a lot of power consumptions. So when we design or considering the location of these multiple data centers, we need to consider those both oscillation stability as well as the voltage stability. And another highlight of our research is the impact of the inertia and motor characteristics. So I'd like to first start from these right figures. So in the baseline case, the WEC system has this systematic inertia at 2.7. And when we implemented the data center in this baseline case, the maximum peak-to-peak magnitude of the oscillation was around 0.2 Hertz. And if you reduce the inertia constant of the synchronous generator within the WEC system, and when the systematic inertia becomes 1.36, we can see that there's a larger amplification of this oscillation magnitude compared to the baseline case. But the interesting point is when we replace the synchronous generator into the renewable energy sources, and since we assume that this renewable energy sources is based on the grid following controller, they do not give inertia or damping or large amount of damping controller in terms of this frequency or oscillations. So the systematic inertia was 0.79, which was much lower than this reduced inertia case. But you can see that in terms of the oscillation magnitude, it was much higher or comparable to the baseline. So this is a very interesting observation because even if the overall system has a lower inertia, it did not lead to the larger amplification of this oscillation. And we think that the reason behind these kinds of this situation comes from the eigen analysis or motor characteristics of the system itself. So as you can see from the left figure, there already exists some unstable modes which have a positive real eigenvalues, like these blue dots. So there are already some unstable modes in the baseline cases around that 1 Hertz, which means that the fluctuation of the at 1 Hertz was further amplified these kinds of motor characteristics of the WEC system. But when we replace the synchronous generator by the renewable energy sources, you can see that these unstable modes are removed, and they have changed it to the higher frequency unstable modes and the lower frequency unstable modes. So even though the system has a lower initial level, there's no amplification by the systematic motor characteristic at these 1 Hz frequencies. So this would be the reason why this high renewable energy source cases has a lower magnitude of the oscillation. And as the
Min-Seung, sorry for interrupting you. In the interest of time, do you like to stop for questions and then see before we move on? Yeah, we might not have the full time for this. Yeah.
I see.
Yeah, I saw there were hands earlier. Maybe does anyone have questions? Yes, please go ahead, Mohammed.
Thank you for this presentation. If you just can shed some light about the size of the data center compared to the size of the system. I didn't get it. Like when you say that the data center can cause oscillation, local oscillation on the system. Are we talking about, let's say you have a system of 200 gigawatt and the data center is 1 gigawatt, for example, or a distributed 1 gigawatt? Like the size is, I think, is maybe if you can just put more light on what is the size of the data center and what is the size of the oscillations that you are seeing basically based on that. Thank you so much.
Yeah, basically we are saying that all the individual data centers are 1 gigawatt, but by differentiating the number of data centers, the penetration level for each system has been multiplied. Yeah, so we assume that the data center penetration level is around 10% of each system, and yeah, for all the data centers, they are set as 1 gigawatt based on the industrial reports about the assumption or the expectation of this each data center size.
So it's 10% from the total load of the system, basically, or the total generation capacity of the system. The total load of the system, this is what you are saying. 10% of the total load of the system is data centers. And at this level, you start seeing the oscillation because what you are saying is critical for the utilities. Like if you have a data center that's causing oscillations, it might cause wide area oscillations is a big thing to claim or a very big finding. But when you say that's 10, only when you reach, it's about when the penetration level reach 10% is a totally different story than just 1% or 0.5%, basically. That's what I'm trying to say. Yeah, so I'm talking about 10% from the overall system. At this time, you can see local oscillations. And I think we're still far from the 10%, but yeah, but this is something we have to work on as the penetration of data centers or the penetration of data center level increases in the grid, basically. Thank you.
Yeah. So yeah, we set the penetration level based on the base load, which did not consider the size of the data center. So it could be a little bit less than the 10% when we set the total load by combining the base load and the data center load. And in the case of the penetration level, I know that in most of the regions, the penetration level of the data centers did not reach the 10%, and it is much lower than the 10%. But in terms of some specific regions in the North America, there are some regions which have a very high penetration level of the data centers. So yeah, and that was the reason why we mostly consider the North America grids for our studies.
Thank you.
Thank you.
Was there a follow-up on this point? Sorry, I heard something. I just want to.
I'm good. Thank you. Very good answer.
Okay.
Thank you so much. Appreciate it. Thank you.
Okay, thank you. So yeah, I think it's clarified that this is a hypothetical scenario with the potential growth in different in data center concentrated regions. So yeah, it's not yet disrupting the grid. Yeah, I want to go to the chat. Han Tao Cui asked the question in the chat box, and Min-Seung, if you want to go see it. So can you comment on the capabilities of the open source Anders simulator? Any additional models or features that may be useful for data center modeling and simulation? I believe this from Professor Han Tao Cui, who is the developer of Anders simulator for this study. Yeah.
So yeah, actually, I really use this in the simulator very well. I think it already have a very diverse operations or tools we can use. So specifically, I think that the eigenanalysis, which the ND simulator provided, was a very good good analytical tool we can use. And I think that when I use the ND simulation, I'm not sure whether I have used the recent ND's versions, but I've seen that there are some kinds of mismatches which we cannot directly use the PSSE, the DYR, or the low files based on the 30 maybe the 35 edition. So if we can, if and this tool is updated to use those kinds of recent PSS in files, I think that would be a great feature we can, and this model and this simulation tool can be improved maybe.
Great.
Yeah,
There's another.
Yeah, go ahead.
Okay. There's another question asked why with high renewable and low inertial, there's still a better frequency handling than the case with inertial at 1.27.
Yeah. So basically, I think that the reason behind why the high renewable energy sources cases has a lower magnitude oscillation is not that the renewable energy sources control the oscillation. So basically, we are replacing the synchronous generator by the renewable energy sources. There are some kinds of modifications in the motor characteristics of the total power system, like the left figure. So although it was not intended changes, the unstable modes which already existed in the conventional system was removed when we modify these conventional generators into renewable energy sources. So you can see that there is no green axis in this unstable modes around that 1 Hertz. So which means that there is no amplification of this 1 Hertz local oscillations by the systematic characteristics. So although it was not intended, there are some kinds of differences in the modal responses or frequency responses of the system, which result in a no amplification of this local oscillations. Yeah.
Yeah. Other questions for Min-Seung? Feel free to unmute. Yeah, go ahead.
So thank you also for clarification regarding the renewable, but I think this is mainly because you assume the data center with 1 Hertz frequency. So if you increase the frequency of the data center, you will see more amplification at the higher mode, basically. I think this is the case. Yeah, but feel free to correct me if I misunderstand it here.
Yeah, that's right. So it depends on the frequency of the data center fluctuation itself, as well as the motor characteristics of the system itself. So yeah, we
exactly.
think that removing the unstable modes, the fluctuations at these unstable modes at each specific system is the most critical thing to remove or help the oscillations stability or oscillations severity.
So far, we have seen data centers having frequency from around maybe a little bit less than 1 to 10 Hertz. This is what I've seen in trying to connect here in our area. But usually in that range is the frequency range for data centers, basically. Or this is what I've been seeing so far.
Yeah.
Thank you.
Thank you for the discussion. Yeah, any final question before we might want to move to the final slide and then wrap up because of the time constraint? Yeah. Okay, so yeah, Min-Seung, please maybe skip the technical part and go to the final slide. Yeah.
Oh, yeah. Yeah, so we also tested how each mitigation approaches affect the oscillation severity, and our conclusion is that removing the fluctuation itself or reducing the fluctuation itself would be the best option for reducing the overall oscillation severity. So we have also proposed some kinds of hybrid energy system and its according controller and the reference designs. So we could stabilize the fluctuation or the frequency oscillation from these AI data centers. So we have also provide how the size of this hybrid energy storage system should be determined based on this oscillation severity. And to conclude my presentation, we have seen that this kind of fluctuation could lead to the series wide area oscillations, but it can be efficiently mitigated by the power-smoothing theoretically collocated hybrid energy storage system. And the key point from this hybrid energy storage system is that according to the size of the hybrid energy storage system, the magnitude of this fluctuation can be controlled, or it can be set based on the size of the hybrid energy storage system. So we would like to further investigate how the maximum fluctuation level of this multiple data centers should be determined to ensure the grid oscillation stability. Yeah, thank you for listening and participating in this task course. So that was my final slide of this break.
Thank you so much, Min-Seung, and thanks everyone for joining us today. As Min-Seung mentioned at the beginning, we will have follow-up webinar. We hope to make it on a regular basis. If I forgot to mention, if anyone wants to present, please let us know. Yeah, we definitely have space to arrange in the lineup for presenting your own work. Also, yeah, there will be more updates on activities at the PES general meeting this year in Montreal. Yeah, so please stay tuned. Yeah, finally, yeah, I hope everyone is on the task force email list. We'll share the slides and also other communications to you. Yeah. Thank you, everyone. Yeah, have a good Friday. Bye.
Thank you.